did the moment at A. That's here. So it's C times 18. Rotation is counterclockwise positive, and 48 times 20 negative. Look good now. Makes sense now. And then you just use your algebra to solve this because this becomes the equation, right? So this statement moves to the other side, becomes positive, and then we divide by the 18 to get 53.33. Well done. Most of you did just fine. Some missed a few little things, like you can't leave the unit off. It becomes pounds, right? We're trying to find the load in the wire. It's pounds. Direction's important, not critical. Questions? Another one on Friday, quiz on Friday. It gets a little more difficult each time. Like we start throwing angled forces in here, then it's going to get a little more complicated. Questions? Any questions on the quiz? Okie doke. Silence is compliance. You know, silence means you don't have any questions. So that could mean I'm not doing my job if I'm not generating a lot of good questions. All right, let's look at the calendar because this is a critical time in the term, believe it or not. So adult education research has proven weeks 5, 6, and 7 are huge. If you can make it through weeks 5, 6, and 7, you will make it through the term. But it's big. Like there's a lot of folks not here. We're down in numbers. Your persistence level has to go up like the next 3 weeks. It's really tough. I'm just saying. Very hard time in the term. Every term, right? It's like in the beginning, you're all excited about the term. You're going to do really well this term. That's weeks 1, 2, 3, 4. And then like 5, 6, 7, 8 are rough. Like, oh God. On an instructor level, this is when we start to feel the crunch. Like I only have so much time left and I got to get through the content. So that's what your instructors are feeling. So they're like going to push at the worst time, like right when you're getting a little burned out in the term. Anyway, I laid the term out for us. This class is pretty nice because it has a follow-up sequential course. So I can pace it as we need it, but that just puts the crunch on next term to make up some more time. So that's not fantastic. But we're going to do chapter 4 the rest of this week, and then it'll end pretty much here. And then we'll go into trusses chapter 5 here. And then week 8 will be trusses again, because it's a big chapter. Like if you look at chapters, it's huge. It has trusses and frames in there, 2 different methods for trusses, a whole new method for frames. It's a lot. So, and they're long problems. Like one problem can be an hour, easy. So like when I review homework, I was going to chew up so much time when we're in trusses. So time becomes short. We'll get through it though, a couple weeks, and then we'll do exam 2. So exam 2 will really be over chapters 4 and 5. And that's it. But 4 is big, equilibrium. We're just kind of into it, right? And then 5's big, trusses and frames and machines, 3 things in 5. Friction, super quick, not too bad. Week 9 is friction. Hopefully in week 9, we can pick away at centroids also, so we don't have 2 chapters in the last week. But centroids and inertia is just a formula, like one formula that I teach you, and then you just got to learn how to run the formula. That's it. So there's not a lot of like, oh, what do I do? It's like, if it's a centroid problem, the question is find the centroid. So it's not like you have to think through things, right? So those 2 chapters I'm not super worried about. And then chapter 9 is what we start in. in strength of materials, and that's stress and strain. Okay, so that kind of lays the term out. The finals here on the 17th. And I think I said you can come early. I'll be here at 7, starts at 8. That's it. I have like 3 labs that I like to do in this class. So hopefully we squeeze in a truss lab with our truss tool, a friction lab with my friction bag. That's over there. So yeah, we'll try and do that too. So it's just not all death by lecture. Good. There'll be a quiz here, quiz 5. There'll be a quiz here, quiz 6. Kind of same rhythm. Homework's laid out for the week. You can start picking away, moving forward. You could start reading chapter 5, like in your spare time, if you want to try and get ahead of the game a little bit. But it's a lot. We'll have a lot going on. All right, let's go over the homework. So it's super important that you do the homework before I go over it. So hopefully everyone's doing that, because you got to struggle with it to learn it. If I just go over it and you haven't struggled with it, it's not a great learning curve. So the struggle is good. 15. Calculate the force in each cable for the suspended weight shown. So, tough problem, because how many unknown forces do we have in the y direction? We have 3 total, 2 unknown, right? This one, F1y, and this one, F2y. 2 unknown in the y direction, right? How many unknown in the x? 2. There's only 2, but there is 2, F1x and F2x. So that means when I write some forces in the x, I'm going to have 2 unknowns. When I write some forces in the y, I'm going to have 2 unknowns. Do I do moments on this kind of problem? No, it's concurrent. So that means I have simultaneous equations going to happen. Some forces in the x, some forces in the y. So it's really good to think through these. That's what you want to think through on every equilibrium problem. You want to think through that first. Like, how many unknowns do I have in the x? How many unknowns do I have in the y? If you only have 1 unknown in one of those directions, that's where you want to start, right? But we have 2 unknowns in 2 directions. Like, oh, crud. Just means write the equations, solve for x and y. All right. So these, you can solve out the components first, so you know the formula, or you can just put it into the equation, however you want to do it. So I'll do this side right here by solving it out. So y is opposite of the 30 degrees, so that's sine. So I can write sine 30 equals F1y over F1. Yeah, everyone see that? It's using variables instead of numbers, but we have to be able to get F1y. So F1y, that's the y component, it's equal to F1 sine 30. And that's what will go in the y equation. Okay, so we're going to end up with the F1 as the variable, which is what we want to know, what F1 is, and F2. So you have to do that for each component, right? Or you just know that this is kind of the format for the component, and you just have to figure out whether it's sine or cosine. Well, the y is sine, the adjacent side is cosine. So F1x is going to be what? F1 cosine 30. So there's the two components for F1. Trigonometry again, since day one, pretty much trigonometry. So once you get that kind of rhythm figured out, then getting this one's not too bad. Sine 45 times F2 is going to be the Y. F2Y. F2X is going to be cosine 45. Since it's an since it's a 45, sine cosine doesn't matter, but I still try to write it appropriately because that's good practice for you. So now we have all those components, we can put them into the equation. Right? I can go, oh, sum, here, I'll use a different color. Really into colors today. Anyone colorblind? Okay, hope not. Some forces in the X. The X, this one's negative, right? F2X. But I don't want to put F2X in. I want to put cosine 45 F2. So that is that component. And then I'll put this one in, F1X. F1X is F1 cosine 30. And it's positive. And all that's equal to 0. It is a lot to keep track of. A lot. Because we have this negative sign, this one's positive, and that's because of the just direction of the forces. Because we're summing forces. How many unknown in this equation? 2. What are they? F1 and F2, the two variables, right? So we can't solve it. That means we need another equation that has F1 and F2 in it. So we go for the other equation. Forces in the Y. I'm going to put the 500 in right now so I don't forget. And then I need the Y components. So there's one of them here. F1 sine 30. And that's going up. And then there's one here. And it's going up. If you want, these are just numbers, right? Cosine 30, you can put in your calculator. So these can just turn into F1 times a number, F2 times a number. Whatever makes it look less complicated to you, right? I tend to just do this, and now when I do the substitution, I'll turn them into numbers. So you choose which variable you want to isolate. I would do the first equation and isolate I probably isolate F1 because it's positive. So then this statement moves to the other side. And I can solve for F1 in terms of F2. So here I solve for F1. So I move this statement to the other side. All right, and move the cosine F2 to the other side, and 45 cosine is 707. So it's gonna be 707 times F2. That's that statement. Other side becomes positive, and I would divide by cosine 30. 0.866, which again is just a number. 0.816 F2. Everyone see that algebra? If you don't, you got to, I want to help. So that means F1 is equal to 0.816 F2. And then what do I do with that? Substitute it into the other equation right there. So I can write the other equation now, minus 500 plus, instead of F1, I'd substitute in 0.816 F2 times, because it's times sine 30. And I'm going to figure out what sine 30 is. 0.5. So it's times 0.5. So there it is right there and right here. And then I got to add, because I need the rest of the formula, 0.707 F2.
You're just rewriting.
I just rewrote this whole formula subbing in. That makes sense? Yeah. So F1 is this black thing, right? The substitution. And I did turn all the trig functions to numbers. So cosine 45 is 707 and cosine 30 is something else, right? 0.5. Now what do we have? One unknown, one equation. This is just a number F2. This is a number F2. Add those two together. Move the 500 to the other side because it's equal to 0. Got to be equal to 0. So again, it's algebra. These two just add because they're apples and apples, F2s and F2s. You can just add this to this. Move the 500 to the other side and then divide by whatever that constant is. So this number is 0.408 F2 plus this 0.707. 1.115 F2. So the next formula would be 1.115 F2 equals 500. That would be the algebra move of adding these together, moving the 500 to the other side. Okay,
To get the 1.5, we have to get the 0.816, 707.
yeah, so this multiplies 0.5 times 816, yeah. So this becomes 408. And then 408 plus the 7 becomes 1.115. Yeah, make sure you, what?
And then you just substitute F2 back into the first equation.
Yeah, so once we get F2, we substitute back into the first, yep. Yeah, if there's any algebra or trig shenanigans there you don't get, you gotta stop me. So I just keep rolling here. Pick F2, sub it back in to this one, and then you just solve it, right? For F1. Put this to the other side, divide by the cosine of 30. Yeah. That was a rough one. Some algebra and some trigonometry. So F2 448, F1 366. So just to kind of wrap your head around that, how much load was hanging down? 500 pounds. So almost 500, 448 is here in F2. And 366 is here in F1. So hanging a load off at an angle magnifies the loads, like dramatically magnifies the loads. Everyone see that? It's an important kind of logical thing, just so you know when you're working with these concurrent systems, what goes on. It's crazy. Like the flatter these get, what do you think happens to the load? Goes huge, huge. As this load goes out flat, and this load goes out flat, it dramatically increases. It's crazy. Oh, you could make a graph. What happens when they go perfectly horizontal? Like, what's this situation? It's just statically impossible. There's nothing to hold the 500 pounds up, right? There's no other Y force. It's not possible. So when the gymnasts do the iron cross, I don't know if you've ever seen it, but they hang from the rings with their arms perfectly straight. You want to say that's impossible. So it is not possible. If they didn't have lats, lateral muscles, right? These things right here that are huge. Like if you see a gymnast that can do an iron cross, their lats are enormous. Essentially, they're building a triangle here out of their body, and they're able to hang that way. But if they didn't have lats, it's not possible. It's crazy. It's still crazy the amount of load is required. Like the amount of load, we'll be able to do this calculation. The amount of load on their lateral muscles is insane because it's not, you don't get your lats out there that far. That triangle's not that big to carry that weight. So yeah, if this is just slightly off, it's possible then, but these can go up to 10 times magnitude. This could be like 5,000 pounds. So if you ever see somebody hooking something up to lift it and they have you know, they didn't have chokers long enough or something. They didn't have the right chokers, and then the right cabling, and they have it super flat, it's just gonna bust things up. Like, those cables just won't take it. It'll shred them. Anyway. All right, good. Good, good, good. Hopefully you learned a little something out of that. Let's do the next. 20. Said the beam shown carries a vertical concentrated loads. Calculate the reactions at each support, neglect the weight of the beam. We had a roller at B and a pin at A. How many reactions does a roller get? 1. Anyone remember what the rule is with the roller? Perpendicular to the surface removed. That's what's key. So if you have a roller and a horizontal surface, we remove the surface and the roller, it goes in perpendicular to it, right? But if you have a surface that's like this and a roller like this, we got to remove the surface and the roller, we're going to go in perpendicular to the surface removed. That's here. Very weird. Yeah, very rare, not common. Right? And then the other one is if you have a vertical wall and a ladder laying against it, right? And they say it's smooth or frictionless, it's like a roller. It'll hold perpendicular to the surface, but it just won't hold up and down. Right? So it's a little bit like a roller. All right. So we get 1 at B. What are we going to label it? BY. How many at A? 2. Which way do you think they go?
Up.
We're going to say up, AY, and somewhere AX. Oops, sorry. And I assume BY going up. Everything's coming down. You have the supports at the end of the beam. They both got to go up. Just looking at it logically, that makes sense. Now what do we do?
Equations.
Yeah, apply the equations. Like if you don't know what to do, I mean, we could think through it first, right? The better we get at this, at forward thinking, the easier it's going to be. So let's think about summing forces in the X. How many do we have? 1. It's got to be equal to what? 0. Just note it. 0. I wouldn't write that formula, right? If it's that simple, I'm not going to write the formula. I'm just going to note AX is equal to 0. All right, how many unknown in the Y? 2. Which ones are they? AY and BY. So we could write that formula, right? We may need it later. Often you do. So I'm just going to write it out. But we thought about it first, and we know there's going to be 2 unknowns, and we know we're not going to be able to solve it. All right, what are they? They're plus AY. You tell me. Plus BY. Minus 5K. Minus 14K. Minus 6K. And what's that equal to? 0. This 0 means equilibrium, right? It means there is no resultant. Equilibrium means there's no resultant left over. We're accounting for all the forces. All right, how many unknown? 2. So I always get students that don't process that in their head, and they try to solve this. Like, I wrote an equation, I should be able to solve it. Nope, you can't. There's 2 unknowns in there, move on. Go go do something else. Okay, don't spin your wheels trying to solve a multivariable problem. It's not gonna happen. What's the next equation or the last equation we have? Moments. Where do you want to do it? A. There's two forces there. That's where to do it. They both drop out. All right, you tell me what they are. I'm going to count for all the forces. 5K times 3. What's its sign? Negative, because it's clockwise. 14K times 10. Rotation. Negative. 6K times 16. Rotation. Negative. It's getting a little repetitive here. By times
Weird.
20. Rotation. Positive. That's the other mistake that gets made. Is students don't put the variable in. Well, we have something to we have to have something to solve in the equation, right? If you didn't put this in, it's just all numbers. I can't solve for anything. So we cannot forget the reactions when we're doing the moments. We need a variable in there to solve for. And it's a force, just like the rest of them. It's rotating the other direction, so it's positive. Set the equation equal to 0, solve for By. If By is positive, I leave it alone. Let it sit right there. And everything else moves to the other side and becomes positive. Right? So that's algebra. That's a number. That's a number. That's a number. It all moves to the other side. Add it up. 15, 140. $251 kips divided by 20 kips. Oh, 20 feet. Kip feet. So all of these are moments, kip feet, kip feet, kip feet. That's 251, and then we divide by the 20. That make logical sense that it's 12? Looking at the loads? Yeah, sure. If we got 14 and 6 is 20, so we have 25 total, right? If the 25 was directly in the center, that would be like 12 and a half and 12 and a half each side. So it makes sense that we're somewhere, it's kind of, I don't know, kind of evenly distributed, I would say. Not perfectly. So yeah, 12.55 makes sense. Looks good. So that's By. How do we get Ay? Yeah, so just take this, plug it in right there, and now you only need to know Ay, and it's just summing forces in the Y, right? 6 down, 14 down, 5 down, 12.55 up. That's got to put it in balance. By's or Ay's got to balance it out. So 25, 25, 12.45. Done. Now we can go to strength materials and we can calculate the bending stress of the beam. Or we can calculate pin diameter needed to hold the pin. Or we can calculate roller compression loads. We can do a lot now. We know all the loads. We can calculate deflection. How much is it going to deflect? That'll be next term. We can choose a beam. How big does this beam need to be to carry 25,000 pounds? That is a lot of load. Over a 20-foot span, that's like putting what? 5 cars, heavy cars. I don't even think cars weigh 5,000 pounds. All right, 5 heavy cars on a 20-foot beam. A dump truck full of gravel going across the little bridge, right? Somewhere in the backwoods. Wow. All right. Questions? It's okay? All right. The grind here, we just keep going. 20. 20? No. 21. Pin at A, roller at B. Huh? Still didn't hear you. It's that fan, or else I'm getting old. One or the other. You gotta speak up. You gotta project, man. X and a Y at A. Is that right? Am I at the correct side? Yeah. And a Y at B? Yeah. And now we know how to label them. BY, AY, AX. Which way do the Y forces go? Up. Easy peasy so far. What about the X force? Doesn't matter because it's equal to 0. Is it always equal to 0? If there's no X force, it is. If there's an X force, though, it is not equal to 0. So don't make that mistake of just assuming all X forces in life are 0. So not true. Okay. Now what do we do? Yep. Concentrate them. Concentrate the distributed loads. How do we do that? Find the area, put the load through the geometric center. All right, so the 1 kip per foot, right? Yeah, so 26 times 1 is 26, and it goes halfway. So this is the 16 mark. 10, it's gonna be in here somewhere. I'm gonna make it green right there. 26K. Right, so it's 13 each direction. How big is this one? Huh? Yeah, so it's 1 times 16. It's not 2. This marks the elevation kind of that load. Right? So it's 2 to here, it's 1 to here. So that means from here to here is 1 kip per foot. So it's 1 times 16, 16K. So it's got to be careful with that. And it's a new thing, so it's totally okay if you muck that up. Now, with that said, look at the problem. So super easy to interpret it differently because look at this load. appears to be twice as big as this load. So if we're like, oh, well, maybe this is 2 on top of the 1. Right? I could read it that way. That's not normally how we do it. We usually do it like this, right? That's 2, that's 3. If that one was over here, right, it would just be 1 on top of the 2. So if you did it the other way, don't erase it, leave it. Because I think it's legitimate, because they made it twice as big. So it kind of looks like, wait, maybe this is 2 on top of the 1. So how'd you do it?
I did it with 32. I did it with.
Okay, leave it, leave it.
I.
It's not wrong. It's I could interpret that way too, for sure. So let's do it that way. Let's make it 2 on top of the 1. So now it's 3. Right? So if you deal with this by itself, it's 2 times 16, which is what? 32. Well, let's make it 32. So that's a perfect opportunity for like an assumption. Now what do we do? Yep. Apply the equations. This time I'm just going to write them. I'm not going to do the x, but I'll do the y. What are all the y forces? Any others? That's it. Okay, repetitive. We just do the same thing over and over for these kind of problems. If it's they're called parallel force systems. If it's a parallel force system, then yeah, you just float through it like this. We gotta do a moment. We're at. Sure. And then we gotta be careful. 32 times 8. And rotation negative. 26 times what? 13, rotation negative. And by times 26. Rotation positive, set it equal to 0. Equal to 0. Solve for by. $22.85. What's the unit on that? The force. And it's going up. And then we just balance our forces by putting it back in this equation. Right? That would be all 3 reactions. Good? All right. Let's take a short break and then we're gonna do some more practice ones and they're gonna get a little more complicated. 10-minute break, actually 8-minute. I'll start up with the big hand on the 9. Oh.
So that one thing is called T holds where they're like
Iron
cross.
I think is what they call it.
Kind of also like
It's brutal. They usually shake like crazy when they try and hold it, because their muscles are just so. And if you look carefully at the pictures, sometimes it's just slightly angled down, just keeping it an angle, you know? But yeah, it's rough. The physics behind it is incredible. Like the tensile stress on your muscles. Your muscles can only hold so much tensile stress, right? So when we do strength of materials next term, we can actually do strength of materials on the human body. Like we can do a tibia fracture. We can calculate the bending stress required to break a bone. It's crazy. Yeah, it's pretty cool. But that's kind of the whole biomedical engineering part of focus study.
yeah, that's true.
Yeah, it's pretty rough. Lucky to hang by my hands, do a pull-up. Get along out to the side, that's not happening.
I don't understand how like when people are crazy athletic. I went to the gym one time. There was this guy, and he was like doing pull-ups where he'd like pull himself up and then like
Yeah,
just casually just all arm strength. And I was like,
yeah,
he was like floating.
yeah, I don't know. People get into it. Well, I didn't pause the recording, so if you ever do watch this, you'll have like a 10-minute silence. Whoops. Oh, well. All right, let's do this one. I think it's number 26 out of the book. So this, for statics, it doesn't really matter that this is overhanging, but it's overhanging, right? It's called cantilevered. It's cantilevered out past the support. So it does change the moment and some rotation. It's definitely hard on the beam. And it's difficult to calculate deflections because we have two different deflections going on. But we don't have to do that this term. We just have to come up with how much load is on that roller and how much load is on that pin. So same rules, just be careful when you're doing your moments because you have a support that's not at the end of the beam. So start with the free body diagram, just like we always have. In a true free body diagram, I would remove the ground and I would remove the supports. I'll work it slowly. You can work ahead of me. My number's good? This little 1 meter was tricky. Makes sense, the BY is pretty loaded. Like it's carrying most of the 9, all of the 9. And then at least half of the 8, if not more. So 14 makes sense. Huh?
I'm getting 27.7.
Do you have the same formula?
Yep.
Same exact formula? 8 times 2?
Times 2, 9 plus 9.
9's negative. That rotation is still clockwise around A. Because you ignore B, right? You ignore all the sports. Just do one force at a time. So it should be negative 8 times 2, negative 9 times 6.5, plus BY times 5. It's good. All right, let's do one more. This one we'll do together. So this is where we're heading when we do trusses. But the first part of a truss is just what we're doing right now, which is finding out what the load is on the roller and what the load is on the pin. So just because it's, got height and width, nothing changes for our approach. It's the same thing. We sum forces in the X, we sum forces in the Y, and we do moments when we have to. Okay? Free body diagram first. So just same steps as we've been doing. So let's all draw the free body diagram first and draw the drawing. So I'll give you some time to do that. You can go straight to just the free body diagram. We never take the truss apart when we're doing reactions. So what we're doing right now is finding the reactions. We leave the truss together. It's one solid object. That's all we care about. This doesn't say something inappropriate, does it? Let's go. How many does a pin get? Gets 2. How many does a ruler get? Gets 1. BY, AY, and AX. Guessing both of the Y's go up because all the load's coming down, right? What about AX? Definitely to the left because the rest of the X loads are to the right. Everybody got it drawn? Or do I need to wait? Are we good? Matthew, you good? Okay. Apply the equations, right? Some forces in the X. What are they? Plus 20K, because it's going to the right. Plus 10K minus AX. And all that's got to be equal to 0. Solve this equation and we get AX equal what? 30K to the left. So for chapter 5, we're going to want to write these up here. Right? This is really where they're at. So this is where we're going to need that information before we attack the truss. All right, I'm just going to go to the next formula. What are all the Y forces? Get them all? When it gets complicated, like you might want to like mark them off somehow. Just don't want to miss one. Got to get them all. So AY up, BY up, 12K down, 8K down. How many unknown? 2. Can't do anything with it. What do we do? Moments. Yep. Where do you want to do them? At A. Good old A. We could do them anywhere, just so you know, but it is pretty common to.
But we didn't want to do that.
Yeah, it gets rid of 2. Gets rid of AY and gets rid of AX, right? Those two don't create a moment about that point. If the force goes through the point, no moment. If the force does not go through the point, it creates moment, and we've got to include it. So you got to go one at a time and say, okay, does this 20K go through that point? Does not. So that means it creates moment. 20K times what? Well, times the perpendicular distance. That's this distance right here. How far is that? Yeah, it's 15. All these verticals are 15, so it's 15 feet. Rotation. What kind of rotation does 20K make about point A? Clockwise, negative. Every force that doesn't go through the point has to be included. What about the 12K? Does it go through A? No. And its perpendicular distance, line of action here, perpendicular distance here, 30. And rotation. I move it down near the perpendicular distance, kind of down in here, and yeah, it's going to spin around that way. It's clockwise again, negative. What about the 10K? I'm just working my way around, so I don't miss one. That's how I do it. I'm gonna go to 10K. Times what? Rotation. Yeah, also negative. What about BY? BY definitely creates moment. And it's times 60. And oops, its rotation is, yeah, positive. And then just working my way around the truss, I have got to 8K. 8K times 45, and its rotation is negative. Just work your way through it. And I ran out of room, so I just dropped down to the next line. The equation just continues. So on more complicated problems, when you got a lot going on, I count the moments 1, 2, 3, 4, 5. Then I count 1, 2, 3, 4, 5. So somehow you have to keep track of which ones you have included and which ones you missed or don't get included. These two don't get included because they're going through A. They drop out. BY equals. Keep your signs straight. BY is positive. I'm going to leave it there. Everything else moves to the other side, becomes positive. Crunch that moment. Tell me what you get. You get that? 19.5? Yeah. So then what do we get for AY? We take BY, we plug it back in here, and we solve for AY. So we got 12 coming down and 8 coming down. So how much is that? 20 coming down, and we have 19.5 going up. So we need another 0.5 going up to balance it out, right? It's good. Do we believe it? Huge load here at B, right? Everyone see that? Tiny load here at AY, almost nothing. Why would that be? Seems like a lot of load out there for nothing here. What's this 10 and 20 trying to do? Push it to the right, but it's also trying to do what about point B? It's trying to rotate this thing, isn't it? About point B, which is lifting it off of AY. even though 12 and 8 are pushing down and AY is fighting that, 20 and 10 are bigger than these two. So the effect of this thing trying to rotate around B and the 12 and 8 pushing down almost completely unloads that pin. It's got a little on it, 500 pounds, right? But compared to the loads, it's pretty much in balance. But that's why that's a pin. Because if we made this 50K, this pin would hold down, not push up. So the question could have been, is the pin holding down or is the pin holding up? Like, which direction is the pin holding? If 10K went to 20K, this thing would want to rotate. That pin would, this would flip over and it would hold down. It's almost zero right now. Does that make sense? So the assumption of this going up was just an assumption. I had no idea if it was going up or down. With these side loads up high, this thing wants to rotate. This could have been holding down easy. If this would have come up negative, right, that would have meant it doesn't go up, it's going down. It's holding down. But that's why that's a pin and not a roller. If it's a roller can't hold down. A roller is just like a BB, right? A ball, a golf ball, whatever, tennis ball. It can't hold down. So the design of this thing with the pin here and the roller here is good for that side load. Questions? These are like the ones you have for homework. Notice that we didn't even think about any of this stuff. We just treated this whole thing like it was a solid thing, right? That's the first step of trusses. Leave it together. Don't take it apart. You're not doing an analysis inside the truss. You're doing an analysis of the external forces. That's our first step in trusses. So that's why we do it in this chapter. Before we go inside the truss, next chapter we'll say, okay, if this is point G and this is point F, how much is the load in GF? Right? That's what we do in chapter 5. It's like, oh, now we got to figure out what's going on inside the truss. But this is your first step, figuring out what's going on outside the truss. And then you're just one step away from being able to design a truss, right? Once we know how much that load is, then next term we'll say, all right, it's got 10K on it in compression. Can we use a 2x4 for that? A wood 2x4? Well, I don't know. We have to figure out the stress, right? We have to calculate stresses. So if it'll carry it, then that's great. If it won't, then we need to put a 2x6 in there, a bigger piece of wood, right? So that's where we're headed. All right, your homework is 23, 24, 35. 23, 24, 35. Good job. Hang in there. Fight the good fight. This is why everybody doesn't go to college. Right? When you're at that party and they're like, everybody goes to college. Nope, everybody does not go to college. And it's because it's hard. And everybody definitely doesn't choose engineering when they go to college because it's even harder. So good job. It's so worth it, y'all.